Anyway, Professor Nikolay Zheludev comes to us from Southampton. He's a very famous scientist in many important fields related one way or the other to nanophotonics and other things as well. Originally, he came from the former Soviet Union. He graduated with a PhD and a DSc. So this is like a second doctorate that is, I don't know if it is, but definitely used to be common in the former Soviet Union. He got it from the famous Moscow State University, and he moved to the United Kingdom in 1991. In the United Kingdom, he's the deputy director of the Center for Photonic Materials at Southampton University, which is, of course, a well-known place. And simultaneously, he directs the Center for Disruptive Photonics at NTU in Singapore. Nikolay received many awards. I will not name them over the years, except to mention that he's a fellow of the Royal Society and a foreign member of the US Academy of Engineering. He's a great friend of many of us at Technion and of the Israeli photonics community at large. And so we are very happy to host him, not for the first time. I'll say a word about the talks that we are hearing today. So Nikolay and I, and some other people, but for sure, the two of us are regular participants in a conference called PQE, which takes place in Utah. This is a skier conference, and I'm not a skier. I'm not sure about Nikolay, but most people come there for the ski. This year, Nikolay didn't come because and same for me because of COVID. So instead of giving plenary talks, both of us get regular talks, which were allowed to be done over Zoom. The plenary talks were not allowed by Zoom, so somebody substituted for us. So I listened, of course, to the Zoom meeting, and I liked very much the talk. And it was a shortened talk, so he couldn't say everything there. And immediately after the talk, I invited him to give the RBNI seminar where we can hear the full story, because we're not limited to 20 minutes. And it took a while to organize it because everybody is busy and so on and so forth. But finally, we are here. So I'm very happy to have Nikolay talk to us about this field called picophotonics, which is new and may become a very major field, or may just be just one more field in the great area of photonics. So please, Nikolay.
Yes, Gadi, thank you very much. So this talk has a provocative title of picophotonics, and I've been pushing for last maybe nearly couple of years now for recognition of this field. And I will give you some examples of what may fall into the domain of picophotonics, and give examples of our recent work in the field. Well, I think that for everybody in photonics community, it's quite obvious that there's a gap in photonic technology which does not cover physical sizes beyond maybe 30 nanometers or so. So we start with conventional metrologies and various sophisticated schemes for improving resolution. Then the gap, and the gap is only covered by electron beam imaging and metrology technologies. And this is extremely interesting gap, which of course has everything from nanomachine to viruses to quantum forces, Brownian motion. And what we wanted to do, we wanted one way or another to enter this gap with photonics technologies. So, however, even the electron microscopy is limited to about 50 picometer resolution with the most sophisticated instruments, in particular cryo-electron microscopy, which is now widely used in biology. So, so there is essentially a no man's land beyond that, right? For imaging, and we here in Southampton and in the NTU in the last couple of years, looked at what is possible with light and electron beams. And if we can actually get through this barrier and see events at a smaller scale. And actually, the first example I will give to you is picometer scale imaging with 3 electron beams beyond this 50 picometer barrier. This will be about visualization of subatomic movements in nanostructures. In fact, technically, this idea is very simple. For instance, you have here a cantilever, a typical example of a nanomechanical device, a typical component of nanomechanical device. What you do, you put it in a conventional scanning electron microscope, and you bombard it with a focused beam of electrons. And if these focused beams can be easily focused to about a nanometer, maybe a couple of nanometers in diameter, but hit the object at the edge of the object, then small displacement of the object, in this case of a cantilever, will give a considerable change in secondary photoelectrons. And therefore, the variation of the signal upon displacement will be proportional to the gradient of the profile of the structure. And if you do very simple estimates, which take into account the shot noise of detection of the electrons, you within about a second can detect a picometer displacement of such a cantilever, which is, of course, an absolutely remarkable number. And I give you an example that it actually works. But before that, I would like to say that once you master that, you can convert it into hyperspectral visualization technique. So in a conventional electron microscope, you have an object which is illuminated with a beam of electrons, and you scan your focused beam, detecting, say, for instance, secondary electrons. And this creates you a static image. In fact, what we do a slightly different thing. We stay with our electron beam in a particular point of the object, which moves, and detect variation, in fact, spectrum of secondary electrons, and then build the image of the object from spectral components of this current. And therefore, if you pick up a particular frequency, you see how the objects look like at this frequency. In this case, the frequency of movement of the wings of the beam. And this is a very practical proposition, and I will illustrate it to you on the following example. So you remember the famous flea by Robert Hooke, imaged in a conventional microscope, which is known to any physicist and is a symbol of Royal Society, actually. So we extracted a living flea from my dog, and then put it in the microscope and put it on a little shaker. And this little shaker, a piezo shaker, excited various mode of oscillations depending on the frequency of the shaker. So this is a scanning electron microscope image, and this is amplitude of movements of the satire of the flea at a particular frequency, in this case in 5 kilohertz. These movements are stimulated by piezo drive, and they are large, they're in the scale of nanometers. You can go much further. You can go into the level of picometers, where you meet a typical amplitude of a Brownian motion in nanostructure. So this is a little cantilever cut from a silicon membrane. And this cantilever obviously has its natural frequency of out-of-plane oscillations. If you put your point of injection of electrons somewhere here, there's a huge gradient, and then you detect spectrum of the signal. You can see this spectral components in the spectrum corresponding to thermal motion of the cantilever at the at the resonance of the fundamental mode and other modes of movements of this nanoscale cantilever. And then you can, using exactly the same technique as I described for flea, you can see image of this cantilever in terms of its Brownian motion. And this is its white image. Here, the scale of events now in tenths of picoseconds. But the flow level of this technique is around 1 picosecond per 1 picometer if you integrate over a second. So therefore, we are dealing here with events in picometer scale detected in a conventional scanning electron microscope. And the only difference that instead of detecting the zero frequency component of the current, we actually detect components which are of interest to us. Now, let us put it in perspective. So this is a periodic system of the elements, and numbers in black are radii of covalent, or maybe van der Waals covalent in this case, covalent radii of the element. And you see that the diameters of them are typically between 100 and 200 picometers. So this is silicon. Silicon covalent radius is about 250 picometers. So we just demonstrated that we can detect Brownian motion at the level of tens of picometers with a flow level of sensitivity of about 1 picometer in second. So we are entering a scale of events which are deeply subatomic scale. And if you do that, you immediately can apply it to some very, very interesting questions. So what is the nature of Brownian motion, of thermal motion of the cantilever? So if this cantilever is in gas or in water, of course, the source of Brownian motion is collision with ambient gas. However, if you put it in vacuum, the Brownian motion still exists, but it is now related to the dynamics of phonon in the system. So the creation and death, annihilation of the phonons create a momentum transfer which moves the cantilever. Now, pretend you have an instrument which gives you opportunity to look at that in a very short time scale. And this is illustrated on the next slide. In this very short time scale, perhaps you can see events between collisions with individual phonons in this case, or at least see a situation where cantilever keeps moving with the same frequency, with the same velocity for some time. This is called the ballistic regime. The ballistic regime was understood to be present quite a while ago, actually, mostly through the effort of Albert Einstein, who nevertheless saw that it will never be a possibility to see ballistic motion in real systems because the scale of events, the scale of momentum transfer velocities and time was not imaginable at the beginning of the 20th century, of course. So in fact, you can do that. So we use exactly the same technology as I've described. We focus electron beam at the edge of cantilever, which was designed to be a bit big in order to reduce the frequency and give us more space in the frequency space. And this is the spectrum of these movements. Or maybe I can start with simply time domain trace. This is position of the cantilever, and this is time. And this is all this complex thermal motion. If you take a spectrum, you will see at the spectrum as it should be through the Langevin theory of Brownian motion would resonate at the main frequency of the system. And again, the noise equivalent displacement here is the range of 1 picometer second. So what is interesting is that you can apply now various analytical techniques to the real time cantilever displacement trajectory and see how actually, what are the statistics of change of velocity of the cantilever. And this is presented on this slide. So this horizontally is interval within which you detect the cantilever from very short to very long. So from 10⁻⁶ roughly seconds to a fraction of a second. And vertically, you plot the mean square displacement of the cantilever. You know that if the cantilever is in a diffusive regime and moves like a Brownian motion particle, the displacement will be proportional to the square root of the observation time. But if it moves ballistically, meaning like a projectile, displacement will be proportional to time itself. And we can see that if your observation time within this rectangle is short, the movement of the cantilever is ballistic, and it's only after that it becomes departing to the diffusive regime. From the same experiment, one can see how the velocity behaves. If you measure velocity now, and after a little while, and this velocity is the same, or very much the same, this is ballistic regime. And indeed, correlation function between velocity now and velocity in the future remains very close to unity, as long as you observe the cantilever to about 10 microseconds. And this actually a very interesting thing, because it gives you opportunity to see real velocity of the cantilever. You test some fundamentals of thermodynamics, and we have written a paper about that. But also, it also has quite interesting applications in ultrafast thermometry, mass measurements, and obviously in understanding how nanostructures move at non-zero temperatures. And so this is an introduction to my talk in a way, and I would like to ask myself a question. So this is exciting to me, at least. Can we do at least something of this optical, right? With not electron beams, but optical. But before that, I will answer a question which is relevant to that. Are there events in photonics which happens on picometer scale, which are of importance for photonics? And this brings me to a class of systems which we decided to look first to study this question. So these are what we call everybody called non-optomechanical metamaterials. We are in particular in Southampton are very much engaged in metamaterials which are created on thin nanoscale thickness membranes and cut by focused ion beam into structure. So this is a typical structure here. It's electro-optical modulator. But what's now important is not functionality of this, but the Brownian motion in such a structure. In such a structure has two advantages, which are very important. The first advantage, this is a system where we couple optical and mechanical properties. And this gives a lot of functionalities. For instance, the mechanical part of the component is highly nonlinear. You know that if you have a beam, a string, for instance, and you display it for more than thickness of the string, it becomes nonlinear. So this is a low frequency but highly nonlinear system, which is coupled to, say, for instance, in this case, to a plasmonic design on the structure, which gives us interesting optical properties. And altogether, they couple into a system which is optically but highly nonlinear. I don't want to talk about that. I'm saying that this is an important example of a structure we shall be thinking about. So what happens with such a structure? This, again, is artistic impression of such a structure, is that it suffers from Brownian motion. And it suffers from Brownian motion, in particular at mechanical resonances of the system. And this mechanical motion propagates into optical properties very strongly for the optical frequencies, where gradient of optical properties very much depends on displacement between the beams. And I gave here some numbers. I don't want to spoil your attention to the numbers, but I gave numbers for a typical metamaterial of this type. And you can see that characteristic magnitude of thermal oscillations at room temperature is about 160 picometers. Anything between 100 and 200 picometers very often can be seen. But resulting fluctuations of this structure result in immediate fluctuation of optical properties of about 0.16%. This is not much, but it is certainly not insignificant. And this can be very easily seen. So we manufacture such a structure, we put it in the microscope, take a telecom laser and see spectrum of the transmitted light. And immediately you see that at the mechanical resonances of the structure corresponding to different mode of oscillation, you see fluctuations of transmitted intensity and reflected intensity as well. And these movements are, as I said, in about 100 picometers. So therefore, it's a very obvious and very simple example how picometric movements can affect optical properties. This is a bit more sophisticated example. So this is a similar structure, but now a metamaterial, which we put into microscope and illuminate by two lasers. There are two telecom lasers modulated at different frequency. And they act on an oscillator of the beams of the structure which makes the metamaterial. And they are deliberately, these two frequencies are very different. One frequency is relatively high, and it's designed to drive the system at the metamaterial mechanical resonance. So this will be this force on the right. But we also apply a much lower frequency of modulation, and this is designed to through the modulation to periodically change temperature of the material. And change of the temperature of the beams change their fundamental frequency of oscillations, simply because of expansion of the material. So we have, therefore, ability to excite the system parametrically and directly, right? And this is oscillate over a single beam of the metamaterial. And you can see absolutely fantastic things. So for instance, you simply detect the thermal response of the system. So this is oscillation of thermal properties as a function of frequency if you observe with a weak probe beam through the system, right? But once you start pumping it parametrically, changing the effective frequency of the system, you immediately see development of the sidebands, the Stokes and anti-Stokes sidebands in the system, which is immediately visible. Then you switch on driving and you see a complex parametric mixture of various frequencies. I'm not bringing your attention to a nonlinear physics here. It is very exciting. What I'm bringing your attention to that this event happens when the system moves and oscillates with picometer amplitudes, right? And in spite of very small movements, you still detect this optically. So optics care about such minor movements. Right. Can we now do this with light? And this is sort of a key part of my presentation. The key part of my presentation. This is a challenge, right? So if you would like to enter picometer scale with optics, you immediately see a considerable problem. The problem is, I take sodium atom. Sodium atom is 350 picometers van der Waals radius of sodium atom. But if you look at the wavelengths of its famous D line, dipole emission of sodium, it's about 600 nanometers. So therefore, wavelengths of optical emission and optical absorption and optical interaction with sodium is nearly 3,000 times larger than the sodium atom itself. So how can we engage any sensible interaction which will lead to a sensible outcome, right? And so our take on that is that we do not use plane waves. Instead, we will look into how such a small creature, like an atom, exist and interact with a highly structured, what we call topologically structured electromagnetic field. And topologically structured electromagnetic fields, coherent electromagnetic field, can be structured on a very, very small scale. I need to say that sort of in a very loud way, in a very clear way, this was first highlighted by Michael Berry, who gave a very simple example. He considered about 50 coherent plane waves at slightly different angles, and then saw what will happen if they interact in free space. And it was quite clear that they create, first of all, singularities in free space, and then areas where gradient of phase has very, very high value. So local K vector is much higher than K vector of individual wave. And this sort of field would hold small areas of energy backflow, where actually they are pinned to singularities, but this is not that important. What is important is that the area of high K vectors values and the zones of backflow can be considerably smaller than the wavelengths of light. And I need to say that we, 2 years ago, we have been able to, for the first time, to actually map in a superoscillatory field the zones of energy backflow and high value K vectors using original interferometry technique. And this are a result of this experiment. So essentially, we have been able to show that indeed gradient of phase can reach very, very strong values experimentally near the singularities, and indeed zone of energy backflow are coupled to that. So in some part of the space, energy goes in the opposite direction from the prevailing beam of light. So, and this gave us an idea that we now shall apply this to metrology and imaging, right? And on the next slide is the first example of how we did that. We applied to what we now call optical ruler technology. So instead of using a conventional physical ruler in metrology, we used a pattern of light which has very, very tiny areas of high values of K vector for metrological applications. I don't want to spend much time on that. I only give you example on how it works. So you have one platform in which you have a laser and a metamaterial which creates complex topologically structured light. On the other side, you have some equipment to look at the slice of this optical field, and you can see very, very narrow peaks of high values of K vector, and you use this as a marker of your ruler. So in a very simple setup, you immediately can get to sub-nanometer resolution for the movements between macroscopic objects. But this is an old result. It's now 3 years old result. But I'm now moving into a different question, a different problem. Can we apply the same idea to metrology and imaging of microscopic objects, right? So the idea is that you have an object. This is in an artistic way is presented by a complex molecule, but it could be anything. And you put it into a highly structured field. And then you try to get some information about the object by moving it across the structured field and detecting scattering. And we expect that scattering when peculiar areas of the field will overlap with peculiar small areas of the object, will have some features, and we want to detect the object through detecting these features. So, and there is a lot of good reason to believe this is possible. For instance, I show you a phase and intensity of superoscillatory hotspot. It's a simple type of lens which, through accurate interference, creates slightly sub-wavelength hotspot, right? But it has singularities flanking the hotspot, and there's one singularity, there's another. I now drop a nanoparticle, which is lambda by 1,000. Lambda by 1,000. You see this? We are in a deeply picometric regime. And then I move it across the object through singularities. And then if I will detect scattering of that at some distance, in this case, about 2 lambda from the particle, I will see that when it comes through singularities and in our area of energy backflow, you see that a change of scattered field is very profound there, and a reaction of small movements in the particle. Movements to lambda by 2,000 is very noticeable, right? And therefore, the idea is to build some sort of metrology and imaging based on this fact. So the idea is very simple. There's an object you want to measure, you want to image, you illuminate it with structured light, topological structured light with singularities, you throw diffraction pattern on image sensor, and you do it a large number of times on object you know about. And this creates a deep learning process, and you can train a neural network then to recognize an object you never saw by the network if it is properly trained. And this is the paradigm of this technique. You cannot imagine any analytical tools for doing that. But deep learning is the way to go. So I would like to show you these results at the end of my talk. But before that, I will show you something which is exactly the same idea, but not yet using structured light. It's a plane wave illumination. In fact, it's simply defocused Gaussian beam. So, but what is important here is that we apply this deep learning process to recognize some features of the object. And the object is here a slit in a screen. And we want to know where the slit is and how wide is that. So what we do, we put it into a plane wave, create diffraction pattern, which is this red pattern here, and then detect the intensity profile of the pattern on the screen and on the image sensor. And we then train the system by artificially created so-called physical training set, which has a variety of slits with random position and random size to educate the neural network in a way that it will develop a deconvolution mechanism for understanding diffraction pattern from unknown slit. Then you show unknown slit and you get the result. It works amazingly well. So, for instance, this is how a size of the slit is recognized by the network, and the slits are subwavelength. They are from half lambda to roughly 10% of lambda. And you see that you have a quite good dispersion of the results, and I will come to dispersion a bit later. And I would like to compare this with something else. This is, again, using the same network, but only detecting total intensity of light passing through the slit, because the bigger the slit will get more intensity, of course. So can we only use intensity? Yes, we can, and it works okay, but still analyzing the entire complexity of diffraction pattern gives a better result. And how good is good? This can be understood on the next slide. What we do here, we have a process involving focused ion beam milling of the slit. We then measure it by electron microscope, scanning electron microscope, and we also measure it using our optical technique with deep learning. So therefore, we have 3 sets of experiments. We can have prescribed value for focused ion beam milling, and that measuring what has happened. This gives us some information of how good focused ion beam milling and SEM are. We can test them, the optical measurements against prescribed FIB sizes, and we can take optical measurements against scanning electron microscope measurements. Trust me that if you have these 3 measurements, you can actually have a lot of information about the ground truth. And as a result of that, you can calculate how well the ground truth is represented by optical measurements, scanning electron measurements, and how well it's correlated for prescribed FIB width. And the results are not surprising. So scanning electron microscope has here a dispersion of about 4.5 nanometers, which is in terms of lambda by 140. FIB is a bit more accurate, but optical measurements apparently are in the same ballpark of accuracy. So the optical thing is actually challenging accuracy of Fox-Tan beam milling and electron beam microscopy. And you can do optical measurements, for instance, at different distances from the object, mapping your diffraction pattern at 4 or more distances. And therefore, these are independent experiments, and you can improve that. And we have improved it to the level of lambda by 260, which beats both of FIB and scanning electron microscope. So therefore, optics based on deep learning deconvolution is challenging electron beam technology. But this is not what I yet wanted to tell you about. What I want to tell you about is that can we make a step further? Can we now do that experiments I started with on detecting small movements of the cantilever, replacing the electron beam and second electron detection with a supracellular light, right? And detecting then scattered light from the structure. And this would be our goal. And here I show you result of this experiment. We have several experiments in this area, but I show you the most impressive, of course. What we have done, we have taken a membrane of silicon nitride and cut it into a nanowire which sits between two sides in a gap, right? So this is all fabricated by Fox-Tan beam milling. It's a very interesting system because you can, by applying electrostatic voltage, move the nanowire in the gap. And the gap is a nanoscale width, and you can control movements of the nanowire. And actually this is presented on this little video, how you move it electrostatically, right? So what is important of this system is that you can do training for optical experiment in situ using essentially the same system you will be measuring for training by applying known voltages. And this is exactly what we have done. We have applied a series of voltages, a large number of voltages, trained the neural network to then to recognize position of the wire. And we did this for two types of illumination, the plane wave illumination and topologically structured illumination. This was, again, a supracellular light field. And the results are presented on the next slide. But before I show you the results, I want to emphasize one very, very important thing. And this is the fact that the neural network, which sees the diffraction patterns of this nanowire, actually cares about the diffraction pattern structure, not its position. And as a result of that, this system is resilient to mechanical movements of the sample and noises, mechanical noises in the system. And this is most important because without this resilience, you cannot achieve picometric resolution. So this is a result obtained with doing these experiments with plane wave illumination, a defocused Gaussian beam. And you can see that we can get here from nanometers to hundreds of picometers, about 100 of picometers. So this is actual displacement in picometers, and this is error in identifying this displacement. So at a displacement of 100 picometers, the error is about 100 picometers. And then this is what is presented here. This is error optical measurement displacement. However, if you can do the same with super oscillatory field, you can have considerably better numbers, about factor of 3 better. So therefore, for small displacements, you can get to the level of 30 picometers. And this is, in my view, is remarkable, and simply because, again, the size of the silicon from which this membrane is made, silicon atoms are 10 times bigger than the displacement we can measure optically. Okay, and this is a slide which again explains how this happens. So if you eliminate with topologically structured light, there will be jumps in the phase, and jump in the phase in the diffraction pattern give additional component to intensity change of the diffraction pattern. This is why structured light is giving you a better result than unstructured light. Okay, so this is on the picture on the right. You can see computer analysis of that fact, showing that the bright yellow blobs appears in the vicinity of singularities, meaning that when you move your structures with singularity, you see a lot of change. Okay, so this is a slide which is very important for everybody who does deep learning analysis. So we know that artificial intelligence is as good as a training set, right? And this is everybody tell you that, and it's quite understandable. And in optics, there are two ways of generating training sets for metrology or for anything else. The first one is physical training set. So you essentially create a large number of similar objects in the same area of shapes and sizes, and train your network on physical objects. So what is the problem with these sets? Is that they're very expensive, labor intensive. You cannot create by, say, lithography or Fox-Tan biomimetics all the objects you might be interested in, so their universality is not good. But the congruency is fantastic. What it means, congruency? Once you created such a set, you put it on your microscope, you train it on microscope on this set, and then any other object of the same size, of the same type, put on the same position of the microscope, will be completely congruent with the microscope, and therefore the system will recognize it with great accuracy. You can go another way in optics. We have Maxwell equations, right? We can compute training sets. So generation of computer training set, for instance, when you talk about the slit, we simply calculate diffraction patterns of the slits at various sizes, various positions. Easy. Universality is good because you can do nowadays very accurate diffraction patterns from very small objects. Enough computational resources is available now for that. But congruency is poor. So you may think you have a good model of your microscope, a good computer model of your microscope. But in fact, it's always not the case. And then when you start using these sets, you very often run into problems of non-congruency. However, mathematics help us, and there are techniques in artificial intelligence of combining that. Combining that is creating a hybrid training sets, which partially consists of physical and partially of computed, and computed and are adjusted to the qualities of the physical training set. And this is a very good way forward, and this is how we are going right now. So it's relatively cost-effective generation of sets, universality become good, and congruency become reasonable. But the last example, what I gave to you, is the ultimate example. Is then when you do in situ training. So you are measuring or imaging the object, which you can in situ of the experiment adjust to slightly different shapes or positions on the same object. Their congruency is perfect, and this is most important thing. With great congruency, you can get very, very, very good deconvolution mechanism of the network. And this is exactly what's behind this picometric resolution with light. Right. So just a summarizing slide before the last one. So deep learning process can provide a training and creating a highly accurate deconvolution mechanism. And there are now a number of articles in the mathematical community which shows that the Fred-Golomb integral, which is essentially the inverse problem of scattering, is exactly suitable and very, very, very nicely suitable to be addressed by a deep learning process on a neural network. Of course, in many cases, sparsity of the object helps. The sparsity of the object fails, and from information perspective, the advantage of this process is that you provide to the recovery process a lot of information through the deep learning process, and this gives you access to very, very good resolution, far beyond the conventional upper limit. And of course, topological elimination helps a lot because it immediately gives access to high value vectors, small areas, and high gradients of phases, which is needed to recognize a small object. Okay, so now the last slide. I have shown that to you in 2 slides before. This is somebody moving my mouse. No. Okay, never mind. We measure displacement of the object at about 28 picometer resolution. But I already told you, but actually it suffers from Brownian motion, right? And the Brownian motion for this particular nanowire at room temperature is about 150 picometers. So how is it possible? And of course, it's very easy how it's possible. Our detection techniques are using photodetectors, which have a very slow frame rate and camera exposure time. And this experiment is more than 100 microseconds long. And this, therefore, what we see, and we see average mean position of the nanowire, and we do not see dynamics. But can we see dynamics? Yes, we can, because the technique I just described is a single frame rate technique, single shot technique. So therefore, if you have a camera which does a high level of frame rates, you can see dynamics. And currently, you can easily buy a camera which gives you, with good resolution, about 1 megaframe per second. And we know very well from our collaborators here in the UK that cameras are coming with 100 frame rates per second. So that therefore, you can now do these measurements optically with a very, very high bandwidth. And we hope that this gives opportunity to study dynamics of picometric scale events at the nanoscale. And this is our trajectory of travel at the moment. So, and the question is, what can we do with optical imaging and metrology with resolution beyond the Brownian motion? This is an interesting question for everybody, and this gives access to something which we have not been able to see before. So, if you talk to a biologist, and they always say, "Oh, the Brownian motion is a four," and they get away from that by cryo electron microscopy. they take their proteins or whatever they study in solid matrix at low temperature, and they do not move, right? But this technique does not require that. You can operate with nanomachines, for instance, and other things which move at room temperature. So this is a little case for picophotonics, the science of interaction of picometric scale objects and events with light. What we can do: picometric optical metrology, picometric resolution, and optical imaging. I didn't have time to that, but we, for instance, are currently submitting first type of papers on imaging rather than on metrology. Brownian motion and optical properties of nano devices, control of their switching and understanding of the functionality of switching and control of that. And of course, this enormously exciting the field of quantum forces, light induces forces, Hamiltonian type forces in nano object, which only happens at the nanoscale, but leads to picometric movements. We can talk about transport of plasmons and electrons through gaps of various sizes, and generally dynamics, light-driven events in nanomachines. And I think that it may have actually real impact on biology. For instance, we again sort of at Nanomatter next week we will be showing how this type of technique based on deep learning analysis of scattering of topological structured light can be used to localize COVID virus. Well, we didn't do it with COVID virus. We did it do with something which looks very much like COVID virus, but is benign. And so therefore, we expect that maybe in the biology community, there will be some application scope for picophotonics. This is my last slide. This is people who were involved, and are still involved in this project. And this is a growing project for us here at Southampton and in NTU Singapore. Thank you very much.
Thank you, Nikolay. Thank you very much.
Thank you.
I'm clapping. I don't know if you can hear. I'm not sure how to do questions in a Zoom talk, but if anybody has a question, just ask. And then hopefully not two of you will speak at the same time. So the talk is basically open for questions. Introduce yourself, please, if you ask a question.
So maybe I'll start. Mayor Ornstein, of course.
Yeah, Mayor.
Hi, Nikolay.
Yeah.
One issue is you mentioned in the first part looking on Brownian motion and thermal induced Brownian motion, and of course the limit of motion is a vacuum type of motion, vacuum state motion. Mm-hmm. Can you think that you can really go to this level?
Good question, and of course, when we started doing that, we considered that. I'm afraid not. Certainly, in type of structures which we were interested from practical perspective, like say photonic metamaterials, it might be very difficult. However, one can engineer structures which are more susceptible to show Brownian motion. For instance, I even had a slide I decided not to show. If you have a cantilever and you start thinning cantilever, thinner and thinner and thinner, at some thickness of the cantilever, its Brownian motion become comparable with its thickness. So meaning that by controlling the size of the object, you can enhance Brownian motion. And for such specially designed one, you perhaps can look at the quantum regime level. But we do not plan doing this yet. And this is off about 4 or 5 orders of magnitude from what we do now.
Okay, thank you. If there is no other question, I can ask another one, but
Go ahead, Meir.
okay. Basically, from fundamental point of view, there is no limit for resolution. Resolution is always the issue of signal to noise. So if you have, you want to make some sort of an imaging of a slit by plane wave, if you have enough signal to noise, you can really image any dimension that you would like. Okay, so if you're going to the structured light, which is, as Barry said, you have in the super oscillation part, you have very small amount of light because a diminishing amount of light in the higher and higher K. So basically, if you want to compare the quality of imaging or resolution, you should compare the same amount of signal to noise between them, because I assume that for structured light, you need much more light and much more sampling in order to get the high resolution. So my question is really, you are comparing them on the same basis.
So this is a very fair comment, right? And indeed, when you start engaging into low intensity areas where the singularities and energy backflow area are seen, intensity drops. And I think that the answer to this question is perhaps not easy, but in my view, it depends on how actually you recover information about the object from your scattering. For instance, on one of the slides I have shown the fact that scattering very rapidly falls in the point where the singularity is, can be used in identifying position of singularity. And this is exactly what a function of neural network is. And I think that this requires perhaps a lot of work, and we are looking into that. But I gave you a direct comparison. I gave you several times a direct comparison of using the same system, exactly the same object, but two different types of illumination. One with a laser which fires on the system directly, another with super oscillatory beam which has all these dips and intensities. Still, the net result is that super oscillatory at the end of the day gives you much more accurate measurements. And this has been confirmed in a number of experiments, and actually in a considerably large volume calculations which are already published. So, but this is based on individual facts. But the total analysis of that is of comparison. The fair analysis of comparison is absent at the moment, right? But at the same time, I don't think that anybody using just very highly accurate measurements of intensity in conventional microscopy can now claim 30 picometers of resolution, but we do, right? So there is an issue there.
Yeah. From practical point of view, of course, you're right. But again, I was asking about fundamentals. But you're right that there is no yet an established answer to really the.
Yeah. So another question, which we are very much looking collaboration with anybody who would like to collaborate on that, is the information theory aspect of that, right? Yeah. And there were quite a few naive papers published in the last years on information theory with regard to super resolution imaging. I think that this requires the presence of singularities requires complete revision of that. And we would be very welcome if anybody is interested to work with us in that.
Thank you, Nikolay.
Mm-hmm.
Anybody else, please? Okay, last chance. Anybody has a question for Nikolay before we say goodbye?
I'm very happy do not have the question, so don't
Okay.
worry about that.
Okay, so thanks again, Nikolay. It was
thank you.
great to hear you, and I enjoyed very much. I assume the large audience did as well. And I'll see you at the end of April in Singapore.
Yeah.
Okay,
Okay.
goodbye.
Yeah.
Goodbye, everybody. Thanks for coming. Goodbye, Nikolay.
Bye-bye. Thank you very much.
Take care. Yeah, bye-bye.
Bye.
Bye-bye.
Thank you.
Thank you.
Thanks.
Thanks, Nikolay.
Oh, hello. Bye.
אפשר, שמעתי?
כן.